Another physics video, yay! Yeah, so I was thinking about another problem, and I believe I have thought of the answer again, so very good for me, from my perspective. So anyway, we got this little bit of a problem, so I'll say it crudely, I think. So here's the sun, let's say, and here's a planet way far away, and let's say it takes 10 minutes for light to get here. So that's like 20 minutes when you add it back and forth for this gravity thing. It's like it's a little dicey, right? Because if gravity's being created, by blocking stuff, and it's taking 10 minutes for the block to get here, then it's going to show up after this thing's already gotten away. And so the gravity is going to end up behind the thing. And, that's not really going to work. See, it's behind it a little bit. But the catch is that all this stuff that's rotating is also spinning. So all the planets are spinning, which is interesting. But the sun is also spinning. So 28 days, as far as we know, for the exterior of the sun. So 28 days to go around. And then you got Mercury, and that's like 86 days, I think. 86 days. And Venus is like 200 and something or other. 200 XX. And then the Earth is 365, and then Mars is like 600 and XX. So anyway, so that's sort of interesting too, is the pattern, and then it gets really strange out here with the big planets that are way the hell out there. But anyway, they're all spinning, so this rotation is an interesting phenomenon when you think about the gravity, because the gravity is based on this directional information, right? So as it's going through the sun, first there's some directional information going this way, which tends to what's the right word for this? It's going to create more of this kind of thing, like diffraction, and then diffraction out because of the spin this way. So the gravity is going to get diffracted as it goes through the sun, and it's going to come out at some pitch angle. So it's going to be a small angle, but I would predict that if I can figure out the math someday, that there's an angle pitch, that works out, it's even for all these things. So there's an angle here that's proportional to the spin that basically essentially creates the velocity of the planets, what the velocity has to be to stay in the orbit, to even get in the orbit in a sense. Because if you don't have that velocity, you won't end up where the gravity is, because the gravity is ahead of you. So the spin of the sun essentially is creating gravity ahead of the object. So the gravity is being sent from here already where the planet will be. So the planet falls right into the gravity. Conveniently, because of the spin. So the induction begins by the object moving into the gravity of the object. The movement in, consumes some g-force, some of these gravitons. Okay, so fewer of them get to the sun. The sun's reaction is some portion of it moves in this direction, ironically, right? Which is probably creating the spin in the first place. So it's gravity that's causing the spin in the objects by forcing some percentage, a very small percent, 1% to 0.0001%, a very small percentage of the sun is moved in this direction by the gravitational tug. That absorbs gravity that goes out the side, of course, and creates less gravity in this forward position to the object. Forward in the sense that it's being twisted by this rotation. This rotation puts a spin on, a change in it. And so the gravity is ahead of the object, and then there's more gravity applied. So the induction happens, and it gets caught up in this what will eventually become an orbit, in the sense that it will start off eccentric and get you know, and loop and loop and loop, and eventually, as things stabilize, it'll get rounder and rounder, presumably. But anyway, that's the progression of orbits isn't really the subject. The important factor was it just fixes this time delay problem with the speed of light. And so I will eventually get to this math and figure out if there is a set angle here created by the spin, a set angle of migration of the gravity, pitch forward, and whether all the orbits match in terms of their velocities that line, if they were all set up, you know, at exactly the same position, whether they would all fall on that exact line of that angle of diffraction. So there's some more. There's diffraction of gravity through spin. So I like that idea of diffraction being caused by spin. I mean, it's an interesting concept just in terms of atoms and the diffraction of light, and so it might be useful for those kind of concepts also. That it's the spin of the electron that is creating the diffraction patterns we see in different effects like prisms and things. Yeah, so I'm liking that. So anyway, it satisfies me anyway on that problem. So I'll put that problem to bed. So we solved two problems: the problem of conservation, in the sense that the induction issue, where the gravity doesn't really exist till the object's there, and it's accelerating and it's absorbing gravity. So it has to have some portion of it has to be accelerating for it to actually be absorbing gravity, to be actually creating a shadow. And now this spin idea that creates a phenomenon that will compensate for the slowness of the speed of the gravity, the change in the pressure to reach the distant object. So now the distant object has to fall into a certain velocity to maintain an orbit, because it has to be going fast enough to catch up to where the gravity is going to be because of the spin of the thing it's gravitationally connected to. So that does make a lot of sense. Explains why things are in these linear orbits. Explains a lot of, why things don't orbit the other way or any old way, why there are these patterns to orbits. It's because they have to be consistent with that spin dimension. And yeah, they can only get so eccentric. They can't get too eccentric off that spin, or they miss their gravity and go away. Yeah. And the gravity hits something else, somewhere else, far, far away, perhaps. As the force does get dissipated as it goes further and further out, it spreads out further and further and further and further and further, and gets more and more minute in its effect. So anyway, yeah, I believe that might solve the problem. So anyway, so yeah, I think that's it for now. That was it. Yeah, that's what I was thinking on. So move on to the next thing, which I don't exactly know what that would be yet. Yeah, I'll have to go through the video again, see what parts are weak still. I guess the nuclear stuff is always still going to be weak, just because that gets so convoluted. Just trying to figure out the internal dynamics of something you have to just imagine. You can't, and you can only imagine it from pieces of information, not a very complete set of information. So anyway, but maybe I'll do some of the Feynman thing with electrons, because the Feynman diagrams are really quite kinetic. So in a way, they're more validation. I mean, it's funny. Ironically, Feynman was against this, theory in a sense. Well, he was against the particle speed changing variety of the theory, not the purely kinetic push gravity, which I'm advocating, which is sort of unique. But it does sort of match Feynman diagrams in the sense that Feynman diagrams just basically do this conservation of momentum. and they're just really an illustration of how photon goes in, arrow goes in, arrow comes out, electron goes one way, light goes the other way, it all adds up, the arrows add up. It's the same kind of vector addition, just it's the more net product of the interaction, where I'm describing more granularity of the interaction. So anyway, that's enough probably. Yeah, I think so. Moving right along. Till next time.